Good afternoon, everybody. Welcome to Deep Learning Demystified. Hope you're enjoying the conference so far. I know it's early and there's lots to see. And I appreciate you taking an hour out of the day to come dive into the fundamentals of deep learning. What is deep learning? How can I use it? How is it different from other machine learning? Essentially, this course today, this 1 hour lecture, is designed to be an introduction to our fundamentals course from the Deep Learning Institute at NVIDIA, where we get you started to basically be able to go out and start solving problems with deep learning. The Deep Learning Institute is in-house at NVIDIA, incented to teach you to solve your problems with deep learning, whether they're problems that are part of what you use with your in Autodesk or other parts of anything that you're working to solve, really. We have a one-day fundamentals workshop that we do at events and with customers. We do deeper dives into deep learning for industry-specific partners like self-driving cars, healthcare, and robotics. And we also have a lot of online hands-on labs that you can dive into, so you can actually start experimenting in deep learning to not just hear about it, but actually get in and see what does it look like when I start to train neural networks? What kinds of problems should I be thinking about that harness the power of deep learning? And so this hour lecture is really designed to take you from the things you might have read about deep learning, some excitement you might have, to kind of a tangible, where do I start? And we're going to start with some definitions, like what are we talking about when we say deep learning? The lecture is called Deep Learning Demystified. I promise we'll leave some mystery. But you likely hear about deep learning in parallel with hearing about artificial intelligence, which is a word thrown around often and with often a lot of excitement behind it. So we should start by defining what we mean when we say artificial intelligence. And that comes from a definition of intelligence. If we define intelligence as the ability to accomplish complex goals, then artificial intelligence is having non-biological help in achieving our complex goals. Artificial intelligence currently is usually related to computing. So computing helping us to achieve complex goals. Machine learning, if we define intelligence as the ability to achieve complex goals, then learning is the ability to achieve more complex goals today than we could yesterday. So it's change in intelligence over time. Deep learning is the harnessing of algorithms that are inspired by the human brain, which allow us as practitioners to take on learning strategies inspired by human learning. So part of the excitement about deep learning is from its potential impact. And part of the excitement about deep learning is that we know how we learn. So by studying ourselves and by being really conscious of how we think about approaching new learning challenges, we're also making strides in our own projects that use deep learning. So with artificial intelligence, we can spend time thinking about the early artificial intelligence, taking computing and writing clear instructions with trees of if-then logic that enable us to solve complex challenges. And we're able to take that to a point where computers might be able to beat great checkers players. But essentially, that would be like your boss. You're starting a new job, and every day your boss hands you a series of instructions with a lot of if-then statements. And your job as someone who's really good at following instructions is to do those things. But as you learn and as you might develop better ways to do them, you don't have the ability to go implement things better. You're still just dependent on whatever your boss is feeding to you. And so really we're saying, okay, if computers can compute, how can we empower them to compute? How can we take what we're good at, asking big questions, and empower our computers to compute? In this lecture, we're going to dive into a few different schools of thought on machine learning at a really high level, because the deep dive will be into, well, okay, if I'm going to start in machine learning, let's do it through deep learning. So we're not going to translate from machine learning experts to deep learning. We're going to demystify machine learning through the lens of deep learning. So you ideally are coming to this lecture because you've seen deep learning in the world. and see a lot of the large challenges that are being accomplished through deep learning are perceptual challenges, the ability to get machines to see and hear. The ability to translate is kind of another level on top of that. For example, early days of Facebook, you'd spend time tagging pictures of yourself. And over time, their model Deepface now knows who you are. So when you have pictures of yourself today, pictures of yourself when you were younger, pictures of yourself from all different angles, their model understands that that's an entity. That thing is you, not just a group of pixels. And it wasn't done through a series of if-then statements describing the features of you, hair color, face shape, et cetera. It's learned through example. You see other examples in the consumer world that are related to like speech recognition or translation. Google released their earphones this week where if you put your headphones on, you give somebody your cell phone, they can speak in their native tongue and you'll hear them in yours. And you can speak in yours and they'll hear you in theirs. So the ability to translate between languages in real time, things that were science fiction a few years ago. So it's exciting in the consumer space. But as we take those things into industry, the ability to identify what part you're missing in a product that you're building based on the learning of every other part that's been built. The ability to take, in the medical field, to take images from MRIs and say, this person likely is a candidate for this treatment because of all that our algorithms have learned from all of the other patients that have been treated using electronic health records. On the far end, when we talk about not just being able to see and hear and translate, but then also to control, when we look at what it takes to drive a car, we're seeing the world around us, we're hearing, and then we're responding. So that'll be kind of fun to play with as we go in. What's the difference between seeing and then outputting something to us as a user, and then seeing and just making a decision based on it? So we'll play with that as we go a little deeper. AI and deep learning are also transforming the ways that we answer and ask really big questions. And this I'm actually very excited about I think that everybody can leave this room thinking about what should we be teaching in K-12 education? What do we need to know if we have artificial intelligence? What's the role of us as researchers, as people who have come to AU to build things? And my answer in a large way is that our questions have to get bigger. Because if we can build tools to get questions answered, then the practice is on how do I find really good input-output mappings, which we'll talk about. So about 100 years ago, Einstein had developed a unified theory of gravity. In 2015, we were able to use deep learning to see it, to be able to visualize gravity in real time. That transition as a step function to an entirely another field of research in astronomy, which is going about 100x the pace of CPU-based research because of the ability to take what we see and scan the universe basically in parallel. And I don't have deep expertise in medicine, so I want to be accurate when I speak to the difference between traditional approaches and AI for medicine. So I'm going to read this verbatim because I think it's important. But it takes an average of 12 years and $2.6 billion to bring a new drug to market. I think we can agree that there are a lot of problems that decreasing the time and expense there would help. So molecular energetics is a field where millions of molecules are scanned to determine how they interact with each other, which would bring down the cost and bring down the time to market. CPU-based methods, so traditional algorithmic-based methods, can process about 2 million candidates per year, but GPU-based deep learning can do that same work in under 2 minutes, retaining or improving on accuracy. So essentially, we're talking about if we can get our computers to be able to see and hear and then generate new insight because of that, all roll with computing changes. I promise this is the last slide where we're in the big picture. What is it? abstract, and we're going to get into the, well, how do I start, and what's happening, why does it work? We're talking about really big problems that we're working to solve, and you might have heard deep learning or AI referred to as the new electricity or Life 3.0 or a fourth industrial revolution. And those things can sound like large claims. What they're based on is that we've got an entirely new framework for knowledge acquisition. And at the beginning of this conversation, we started by talking about intelligence as the ability to accomplish complex tasks, and then learning as the ability to increasingly complex tasks. We have been learning for a very long time. Early, it was over a long time scale. So a plant wants to accomplish the complex task of surviving in an area without much sun. So then learning looks like bigger leaves. So over multiple generations, we can learn to achieve more complex goals. But it took a long time. The time horizon was multi-generational. Eventually, that led to the brain, which enables us as humans, or other animals as well, to, within one lifetime, learn from experience, be able to accomplish more complex tasks today than we could yesterday. And we see that with a child born 1,000 years ago who might have grown up to be a blacksmith, with the same hardware, can now learn to be a deep learning engineer. Add on top of that a new framework where we all now work together and share our knowledge through technologies like language and the written word. Machine intelligence is a combination of the second and third, where we can have a machine that can go read all of Wikipedia and then generate new insight that's specific to our problem or the question that we're asking. So what's the difference? What is the difference in my workflow? How do I think about working in deep learning versus working in traditional programming? If we wanted to solve a problem in medicine or solve a problem in construction, you want to be able to write an algorithm that recommends the right part at the right time for someone who wants to build something. The best way to do it traditionally would have been to study deeply what are the if statements. If this happens, we should do this. If this happens, we should do this. So to develop domain expertise, and then to write those instructions in code, to be able to take your expertise and share it with the world. Deep learning looks like more of an end-to-end flow, where as a practitioner, we're responsible for only inputs and outputs and then network selection. So we trust our networks to be able to identify the right solution, and our job becomes the teacher. Our job becomes identifying what is the data, what is the experience that I should provide to my network. And so to feel that pain of the traditional way of approaching something for a minute, we're going to play in computer vision. So the ability to teach a computer to see. And on this bottom part here, we know something about that image over there, but we don't know, maybe you don't know what dog that is. Maybe you don't know what breed of dog that is, but based on your own experience, you've learned some things about that. And your job is to explain it to somebody or something that cannot see. A computer cannot see. A computer sees this as raw pixels. I'm going to put a challenge out to the room, and I'm going to actually ask you to talk to each other for a minute, and you're welcome to talk to each other. If you want to scribble on a piece of paper, you're welcome to do that, or you can just think this through to yourself. But I'm going to give about 30 seconds. How would you give instructions to someone to draw this thing that you see in front of you, or recognize what it is in relation to other things? And I'm going to challenge you on the medium part here. And the challenge is, can you make that so that it's only this thing? So it doesn't have another thing that it could be. So with that, I'm going to stop talking for about 30 seconds and encourage you to talk to each other. Describe the thing you see in front of you without using, just from geometric primitives, like shapes. Go. I'm going to interrupt you. Does anybody have a description that you'd like to share?
Not smart enough, sorry.
No is okay. You can see the challenge. And computer vision experts have played for years around how do we go about doing that? And they really creative approaches like identifying that things that are rounded are more often found in nature, where things that have hard edges are more often made by humans. And that is a first node in a really, really deep tree of decisions. Or even like playing with vectors, where like if you move through a space that has a pixel value of x, and if you hit some increase of pixel value, then you've found the object. Like, people have had to get very, very creative. But we look at that and we take our current understanding of the world from our experience from birth of identifying what that thing is. But really, all that we see there are pixels. And the light is reflecting off it. It hits our eyes. Our eyes send a signal to our brain, which processes it through a model that we've built over 30, 40, 50, 60, 70 years. And we know mostly what that is. The deep learning model is more like ours. It's not exactly ours, but it's more like ours. So we're going to play a game. We're going to learn a little bit more about this thing. This thing is a dog, and it might be, and it's named Louis. Sorry, not this thing. I'm going the wrong way. See, the up and the down just got me. Now I'm giving away answers. That thing is Louis. So we want to be able to identify, build a model for ourselves about where is Louis in the world. We're going to do this like a deep neural network would have to do. The first time it sees a new piece of data, in this case it's an image, it could be a word, or it could be a sound signal, or it could be an architectural drawing. It doesn't matter what it is. It's architected to be able to output something very specific. So in this case, I'll give you the same rules. In this case, you have to output a probability of what that thing might be. 1 means it's definitely Louis, you are 100% sure. 0 means it's definitely not. And 0.5 would mean it could go either way. I know that I pressed the wrong button here, so you might know already. But you'd have to make a guess, just like a neural network would, with no background information. Granted, you'd have some. You know that's a dog. All that a computer sees every time is some raw pixels. So whether to yourself or to the person next to you, between 0 and 1 is that Louis. If I hadn't shown you the answer, you might have said something like 0.5. You'd have an error. You'd be wrong, and that'd be OK. But you'd learn something. You'd find out, yes, this beagle is Louis. You'd see another image. Now you know a little bit more. Your mental model has shifted. I'm not a neuroscientist, so I'm not going to tell you what changed in your brain. But connections were made different between when you didn't know who Louis was and now that you got that information. You see another image. I promise there's not more than like 6 or 7 of these. You make another prediction. You find out that's not Louis. So you find out this data set is full of pictures of beagles. It's not just pictures of this Louis is a dog and other things are not dogs. So you have to find out what you're comparing to. See another image, and you make a prediction. Feel free to share your prediction. And you get some feedback. We could ask some interesting questions about what you predicted and what features here led you to predict that thing. And some of them might be things that we know as humans that a computer might not know. But let's keep going. Is this Louis or not Louis? That is Louis. I'll go a little faster. Louis or not? I heard someone say 0, so their loss is 100%. I think this is the last one. Louis or not? OK. That's our data set. Do you think you could do better if you got to see those images again? Probably. Let's transition and see a deep neural network take on the same challenge you just took on. So this is a tool called Digits. And I wanted to start here to not be all that confusing. So what you're looking at right now is you've got a data set with 16 images of beagles. 8 of them have Louis, 8 of them do not have Louis. And we're going to go through one epoch, which means that this neural network, which I'll show you in a second, is going to do exactly what you just did. It's going to see those 16 images, and it's going to hopefully learn something. I can pick a student. In this case, and by student, I mean my neural network. A lot of folks come to start thinking about learning deep learning, and they start to think, well, I need to get a PhD in math and physics, and I need to be able to design and neuroscience so that I can build neural networks. And that's not true. A lot of wonderful, powerful neural networks have been built and designed, and like this tool, you can just click on one. Sometimes you have to maybe go to a website and copy and paste. But you can start, we'll talk about that soon, without knowing anything about the brain. You start in the role of a teacher. So we're going to pick AlexNet. I'll talk about why we picked AlexNet very shortly, and I'll give it a name. So I'll call it one, and we use the word epoch. That means one trip through the data. And I'm creating a neural network model. And it's done. I promise I'm not glazing over this for any reason except for the fact that we're going to go deeper into it later. I don't want to show it until we're ready. And then we'll take a look at an image of Louis and see how it did. Remember, it's seen these images as many times as you have. But it didn't know what a dog was before it started. So you can see that its guess, its initial, I'm calling it initial because 16 images is a very, very small data set, and one epoch is very, very small. But it output just like I told you to output. You had to output a yes or a no. Here it said, let's just split the difference. Basically, it's wrong. So essentially what we've got is an untrained neural network that has an architecture. That's where it starts. This architecture is predefined. And in this case, you've got outputs that are mandated. We've said there are 2 classes of things that this neural network is working to differentiate between, Louis and not Louis. We could do this for handwritten digits, 0 through 9. Then we'd have 10 outputs. The probability of each of those things. We could have 1,000 different classes, all different types of parts that you'd need to build something. And these end 2 nodes would be the outputs, but the probability that the person would choose any of those. At the beginning, you have the structure of the input. In this case, it was a 256 by 256 image with 3 channels for red, green, and blue. So numbers as the input, numbers as the output. And in the middle, math that is designed to learn about images. I promise we'll go deeper there. And it's untrained, so think about this as this thing is designed to learn about images. And then it's exposed to data. It's exposed to data so that it can say that the connections between all of the math have a weight associated with them. And that weight changes over time. That weight changes with experience to say, yep, I was right, or I was more right this time than I was last time. Let me go further in that direction. And what we're looking at is a really simplified version of a neural network. Really, there might be hundreds of layers, hundreds of thousands of different parameters and weights. Maybe a training data set full of pictures of Louis and not Louis, and it's going to make some prediction. And then the model can go out in the world and make predictions using what it learned. Just like if you just felt like you learned who Louis was, you could go out in the world and you could go tell the world who Louis was, or identify him in the wild. let's come back to our model for a second. The first thing that each person, that you all wanted to do when you first saw us, when we first trained, was you said, I want to see this again. If I saw the data set again, I could probably do better. So this time we're going to take the same network, AlexNet, and we're going to run it 100 times. This will take about 2 minutes, and we'll keep moving on while we talk about it. I've got to select the data set. And now we're going to watch, now our network can go a little deeper. I want it to start so we can watch what happens. So originally we have a loss. So the loss is really fundamental to how our network learns, which we'll talk about very shortly. But at this point, what we've got is our loss is how wrong were we? So when I predict Louis, when I predict 50-50, it could be Louis, but I don't know anything about who Louis is, so I'm just going to guess 50-50. My loss is 0.5. I want my loss to go down over time as I learn. Sometimes I might need to see new images. Sometimes the data set is skewed. This is kind of a contrived example because we've got 16 images. You would never train a neural network on 16 images. But we saw this decreasing loss function. Something broke because we have 16 images. And we're going to watch it continue to decrease. In the amount of time that we do this, so we're at 26 trips to the data right now. We'll come back over to our slideshow so we can make sense out of what's happening. We'll come back to there in a few minutes. What these networks are, I'm going to come down so I can show you what we're looking at here. These networks are inspired by the human brain, but they're very, very simplified. Again, you've got the input layer of maybe the pixel values or each word in a sentence, and you've got some output layers. The inputs can really be anything that can be quantified, and the outputs are also anything that can be quantified. What you're doing is you're really creating you're saying, I want this group of things to be as inputs, and this group of things were the corresponding outputs, and I want you, neural network, to learn the map between them. But it's not close to the complexity of the human brain. The human brain has millions and millions, if not billions, of connections, and our most complex neural networks have hundreds of thousands, if not a million. They're getting larger and larger, but really the reason that they're able to learn quickly and to be powerful, the first reason is the ability to compute in parallel. So say we have an image that's 28 by 28 or 256 by 256, or all of Wikipedia, which has who knows how many articles, but have X number of words. If I can read all of those articles in parallel, or if I can look at every pixel in parallel, if I can update each of those weights in parallel, then I'm able to take those 400 or 500,000 different parameters and learn them very quickly. If I tried to do that in series, which is what a CPU would do, you'd have to run loops through your program, and what could take years with a GPU can take hours. So the ability to do this at scale, the ability to work in parallel is a huge factor in why you're starting to see deep learning everywhere. If your one GPU isn't enough, you can fuse them together and have more than one. And that lets us take 100 trips to the data and run them in a little bit less than 3 minutes. Where you can see that the loss started at 0.7. I'm going to say loss. I'm going to use loss as a unitless term right now, which is just the distance from the correct answer. You want the loss to be close to 0. Down to, by the end, 0.04. And that's the average loss for its predictions. And we can go look at that same picture of Louis or a different one. Let's grab a different one for no reason. And we can classify it. And now we've learned something. Yep. So it's built a model, and now that model's fixed for, I can go deploy that model today, next year, et cetera, and it will consistently be, it will use the same model. And it says 100% sure that's Louis. So it's now very, very confident that is Louis. And that is Louis. Louis is my dog. That is Louis. The difference now says, OK, we have these deep neural networks, these very deep algorithms that are inspired by the human brain, but they're not as complex. So what we need to do is we need to do 100 chips through the data. This room wouldn't have wanted to do 100 chips through the data. So our first real characteristic is the algorithm, and the second is the ability to compute in parallel. The third, though, is this. Actually, let's before we go to the third, let's make sense out of how it learned. If you've read into deep learning at all, you've likely seen a lot of these type of diagrams which look like they mean nothing, and they mean a lot. So it's worth kind of starting to play in them. But essentially here, again, you've got inputs. This could be the pixels of an image. These could be words in a sentence. These could be any quantitative thing that you could possibly want, that you could possibly have. And you've got connections between them. And usually, this is the simplest network you could possibly have. It's got one hidden layer and then an output. And you want the mapping to create, like you know what the solution should be. So in this case, maybe this was a picture of Louis. The output should have been 1. But it's wrong. Here it output this light blue, but the target should have been this purple. There's an error, which is we're going to quantify it as 5 for a minute. What will happen is each of these connections then, we can change it. So we change that. We make it a little bit larger. And we find out that when we made that a little bit larger, we had a larger error. So we don't want to go that way. Instead, let's see what happens. When we make it a little bit smaller, our error decreases. That's what we want. We should do that. And we do that in parallel for every single connection, every single one of 500,000 connections in parallel, over and over again. And we call it stochastic gradient descent, which you might know, to identify a increasingly better and better solution, so a local minimum. We try to demath this lecture as much as possible. There should be an equation here that it's just for, if you want to play with the math of it, it's for each of these, our algorithm is saying, take the derivative of the error with respect to each weight and change the weight by that much. So you're just riding down a negative slope until you find the ideal solution. And you do this over and over again. You forward propagate, which means you take an image. Here's my image. You run it all the way through a network. You get some output. You take the loss, and you propagate it back through your network. You change it, and then you go do it again. And you do it again, and do it again. We just did it 100 times. We'll come here in just a minute. Let's see a problem with what we've done so far. Actually, I'll ask the room. Can anyone see a problem with what we've done so far? We memorized the pictures. Where'd they come from? With you? Yeah, absolutely. We memorized the pictures. And you don't see what I see. I'll change that. So if we tried a picture that was not in our data set, it's called overfitting. And what we can't do very well with human learning, this is a problem with human learning, actually. So this says it's not Louis, and I know for a fact that is Louis. Like, it knows nothing about Louis. It knows its data set. You had 16 images. So nice that you can learn your data set. Maybe some of you had classes growing up where they teach you some things and they want you to come take a test and just, can you do the things I showed you how to do? And if your answer was yes, you passed that class, but you left there saying that was not real learning. I can't apply that to the real world. So we're aware of that. And so we'll play with how do we fix that problem. So there are a lot of different tribes in machine learning, coming from anything that you could think through of how did I learn about those, who Louis was through flipping through those images. Was it through logic? Was it through neuroscience? Was it through evolutionary biology? Did I use statistics? Is there a psychology element to it? And really the answer is all of the above. And historically, all of these different methods, all of these different schools have performed similarly. What you're looking at here is you've got performance, which can be measured in accuracy, could be measured in a balance between false positives, true negatives, however you're measuring performance, over how much data you're feeding to a network or feeding to an algorithm, whether it's, again, these were from any of these different tribes. And they were pretty fairly well matched. And the 2010 timeframe came along, and we had a breakout. And the breakout was, actually, I'll pause for a second, let the graph speak for itself. When we call out deep learning, we're talking about a large neural network. And you're seeing a difference in not just the time, but you're seeing that it takes more data. We're looking at a larger data set, larger data sets. So when we talk about the three real components that make deep learning right now on the tip of everybody's tongue, there are three things. It's big data, the GPU, and these deep neural networks. And we know, like, the amount of data that we have access to today is through the roof, right? We're giving off data right now. Google knows where we are. Autodesk knows which section we're in. Maybe next year we'll have a suggestion. You should go see this section because of how you rated this section, the other section, the other section. We have more access to data. We can process it in parallel through these deep algorithms. And what that's enabled is, first, research. So researchers at universities all over the world and tech companies have started to create better and better algorithms. In order to do that, people who want to facilitate that research because it helps them do their work, we've built these technology and frameworks, the ability to not have to learn how to program a GPU, but I can write it in high-level code like Torch or TensorFlow or Caffe, which is human readable. I want you to multiply here. I want you to learn fast. I want you to learn slow, so that we can start playing with different models and different learning environments. You've got access to GPUs in the cloud, in every single cloud service. And now we're starting to say, okay, what kind of problems can I solve? And that's hopefully why you're here, is the question of, do I need to be able to construct neural networks to solve problems? And while the answer is yes, depending on the problem you want to solve, the answer doesn't have to be. We can stand on the shoulders of giants and start to answer large questions. So let's see success before we move on to how you might want to engage. I think I have to escape. Cool. promise that this is not the workflow that you would need to do if you want to take one of our labs. While it's spinning up, actually, I'll show you our lab. So this is the DLI, the Deep Learning Institute. We spin up a GPU for you in the cloud, and all of the tools you might need. In this case, like digits, will load you a data set to play in. And you can start like experimenting with what happens when I do this, what happens when I do that. Let's start it going before we move on. I apologize. Okay, just get it going, and then we'll talk again. So what I'm doing right now is I grabbed a data set. I grabbed a data set. I don't have 60,000 images of my dog. If I did, you could laugh at me. But I do. There are data sets online that are open source and very available. This is called the MNIST data set, which are images of handwritten digits, the numbers 0 through 9. And there are 60,000 of them here. And we're going to run it through a different network. We're going to do it 4 times, so not very long. And what I'll show you is that it learns a generalizable model. So I'll call it general. And it's still going to keep training, it's going to load the data set in the background. So that'll come up soon. While we train, let's play with, in the sake of time so we can make sure that you can engage. I want to make sure that I show you how you might start engaging in this process. At a very high level, you can start to solve problems with deep learning by thinking about deeply learned functions as functions. Meaning, if somebody has solved the problem that you want to solve as part of your solution to something. For example, the data set that we're loading right now was trained by Jan LeCun, who's now the director of AI for Facebook. And hundreds and hundreds of hours, millions and millions of dollars, to be able to classify handwritten digits for the US Postal Service. If I'm a startup right now who wants to create a tool for math teachers to be able to automatically grade their homework and know what numbers they've written, I don't need to go train a deep neural network or learn network architecture. I don't need to even collect the data set. Instead, what I can do is I can go onto something called a model zoo, which I'll point you to in just a second, and I can grab the network architecture description and the pre-trained weights. Those are the 2 things that make up your network. And then my core skill is programming. So what I need to know to engage here are what input does my network expect, and what type of output does it generate? Because if I can create this input anyhow, through any type of traditional programming or computer vision, if I want an image that's 28 by 28, I just have to make sure I have an image that's 28 by 28. That's the type of constraint that I'm talking about. And then what kind of output I get. So in this case, you got an output of those 2 classes, a probability of yes Louis, probability of no Louis. So that then you just have a vector that you can do whatever you want with. So at this level, deploying learned functions, your skill is as a programmer and a problem solver. I'm going to show you one of these model zoos so that you can see what I'm talking about. Searchable without exaggeration through just searching for, like, I'll show you how I got here. But if I type in model zoo, and Caffe is the framework that I play most in, what you get is a table of contents with a lot of different models that do different things. I've got one here which does emotion detection. So I'm an educator, so if I'm thinking about, are people bored by what we're doing today, or are they happy, are they engaged, I might think about deploying this model. And the model I can see, and we haven't played much in it, but this here is a description of the network architecture. And I can copy it without understanding it. And I can come back into the tool I've been using, which is digits. And I can ask for a custom network, and I can paste it there. And now I have the result of their research. I think this might do something. If not, that's okay. You have to trust me. While we've got that going, let's take a look at how we did with our generalized function. So here's our generalized function, and I'll show you a trick that we used to how we can see that this thing worked. We have that same loss function, right? So that blue curve is, it started out having no idea what a number was, dropped off a cliff after seeing, remember this is 60,000 images, so about, I don't know, an eighth of the images, it knew what a number was. And then it was just refining what that number was. This green curve here, and if you wanted to play in deep learning, this is incredibly important practice, is a validation data set. So it's data that the model has not seen or learned from, and it's checking, does it work on new data? And here the answer is yes. We can prove that by showing that network was trained on a bunch of black and white images. And we can upload a not black and white image. Let's do it this way. So we can upload a group of images. And I know you gotta trust me that these were not in the data set, but they're very different than the data set, actually. And what you see here is the image that was a 1 was a 1. A 2 was a 2. A 3 was a 3. A 4 was a 4. A 7 was a 7. I know you see this 8 is a 2. We'll talk about that in just a second, I hope. And here's what we're actually getting. I'll come back to that other section. But the images look like this. They're these color images that have nothing to do with the data set. The original data set were white numbers on black backgrounds exclusively. And so it was able to learn through a large enough data set and a diverse enough data set how to find all like numbers everywhere. Remember this 8 was a 2. We could play, the reason this is interesting is because it's really a 0 reflected on the water. And more important than images, this is interesting because as we start to solve problems like that maybe humans would have classified incorrectly, we start to talk about in narrow fields where AI and deep learning are having superhuman levels of success, which become really important and interesting and feels like medicine, et cetera. So let's make sure that we play with just, I'm going to do no more than 5 more minutes of me talking at you to make sure questions get answered. Otherwise, I'll definitely stick around afterwards if people want to do questions individually. But I'm going to go through these a little bit more quickly. So the first way to engage is to just grab someone else's trained model from the world and just deploy it, build around it, understand its input, understand its output, do whatever you know how to do outside of it, and just say, I have this new capability. Second is you can grab these existing networks, so the architecture is there, and you can feed it new data. So my network that's designed for emotion detection, maybe that can also be used for focus on for people who are driving. Here, the core skill is data science, and your mindset is that of a teacher. How do I present the information? Does the network have the right information? So what we just saw was taking all the data that thing was trained on, looked like this, and we were able to succeed with data like that. And we already saw this. The last way of approaching this field is through, it's a new capability that you can build networks from scratch. The networks are just math. And they're each layer is a mathematical operation. And what these essentially are is they are deeply composite functions. So if we think back to high school algebra, you have f of x. We've got here f of g of h of I dot, dot, dot of x, where the input of each layer comes from the output of the layer before. And at each layer, if we have a deep enough network, the theory is that you can approximate any function. You can, and we'll play with that in just a second, but the layers are combined to describe the architecture. You can describe it in these different frameworks, but the constraint is the output of each layer must fit the input of the next. So as you start to experiment, before you start experimenting, the data has to flow. And we call the data tensors, so Google's framework is called TensorFlow. And it really is the mindset to start with. How do I make sure that my tensor can flow from the input that I have to the output that I want? In all of these, you play with, well, what types of problems can I solve? I have data like text. I have data like images. I have data like video, data like audio. That input data has very different shape and characteristics. I have to think about, is my world static? An image that's a dog is a static image, but learning about language has a time series component to it. If I'm going to predict something in the future, I have to have memory. So what type of layers, what type of math am I going to use? You can learn that through project, but there's some very high level. General reasoning. So general reasoning means I can take any input to any output. And if I have enough of them, I can brute force my way to some kind of useful conclusion. And the math is just matrix multiplication. So if I have input, which is a 28 by 28 image, I can multiply it by some matrix with random values that are eventually learned and learned and learned. Those are the weights. So eventually, I get an accurate mapping of input to output. So if I go deep enough, I can create this mapping. I don't have to do the math to create the mapping. I just show the data to a network. In studying the brain, people have found that this thing called a convolution emulates what happens when we see light with our eyes, and then how this light experience moves through our brain to generate some kind of inference about what that thing is this convolutional neural network that takes raw data, starts to detect low-level features like edges, vertical edges, horizontal edges, diagonal edges. And then each layer, based on how the math works, and I encourage you, just look up convolutions to play with the math if you want to go there, takes larger groups of pixels to inform from edges to face features to the actual face, and then declare, that is my face. That is my face when I'm happy. With time series data, you end up working with these things called recurrent neural networks. And when I say time series data, I mean like language or the stock market, things that change over time and you need to remember. It's just a different type of math. You actually, to start doing it, you don't need to know exactly how an LSTM is built, but you need to know that for language or time series data, you should use them. I've been throwing around the word frameworks. A framework is how you interact with. It's how you describe things. A network is the thing you've just described. So like AlexNet was the thing that just learned. It was described in a language called Caffe, and we used digits to do it. So you'll start to see frameworks be talked about. People really like to start with, well, what framework are you using? I think more important, just don't fret about that before you start. Just start. I'm going to go a little deeper for the sake of time. NVIDIA's involved. I want to make sure that I end with how to start. There is a ton of content online to learn deep learning. Coursera, Udacity, edX, Stanford online courses. There's no shortage of places you can watch videos about how how-to deep learning. I think that with the NVIDIA Deep Learning Institute, what sets us apart is that you can start, but you're still starting on our contrived projects. You're not going to get stuck. We're going to walk you through every step of the way. It's nice that you get to have a GPU and see a training curve and change something and see what happens. But I implore you, if you're interested in this, to grab a project. Doesn't matter what it is, because then you'll get stuck and need to go out in the world and learn it. All the information is out there. My project right now is I have a cat that does not, or that brings in dead animals, and a dog that does not. And I have a doggy door that I want my dog to be able to use. So I have a cat-dog detector that can tell me when Louie's there and when Nala's there, and it lets Louie in and does not let Nala in. And that's what I'm battling through right now. So I get to learn things like object detection. How do I even build, like, how do I label data for object detection? There are a lot of hurdles to jump through, but with like anything, early in learning about something new, it's very slow, but it really does start to, like, as you learn the framework and you learn the tools and you learn the syntax and you learn how to label, it really is very, very fast to ramp up. So I implore you, if you're interested in deep learning, play in the Deep Learning Institute stuff, go online and watch videos, but you have to be creating because that's when you'll get stuck and that's when you really start to gain new insight and new capability for yourself. So with that, I will stick around for questions, et cetera. But thank you.